going to use the Hessian of a function at a critical point to characterize whether that critical point is a point of local maxima, minima, or a saddle point. So the setup is as follows. F is from BAR to the real numbers. It's a C2 smooth function. We are assuming C2 smoothness so that we can take the Hessian. That should be clear. Now what I'm going to do is I'm going to also assume that A is a critical point. Now we will invoke this assumption a bit later. So for the time being, we are just going to use the C2 smoothness part of F. Now what we are going to do is we are going to Taylor expand this function f about the point A. We already know that for points near A, we can write f of A plus h is f of A plus h dot grad f at A divided by 1 factorial, which is just 1 of course, plus h dot grad squared f at A by 2 factorial. And here I cannot just put A, this is actually going to be that error term. I'm using the Taylor's theorem with the reminder. So I can only say A plus T naught H, where T naught is in 0, 1. So this is what Taylor's theorem would tell me. I can approximate the value of f at the point A plus h using the value of h dot grad of the point f at A plus this second order term h dot grad squared f of A plus T naught h, where T naught is a point in between 0 and 1. Now a straightforward and utterly easy computation will tell you that this h dot grad squared of f of A plus T naught h, this mysterious quantity, is none other than summation I equals I comma j running from 1 to n di dj f of A plus T naught h multiplied by hi hj. Okay, so I leave it to you to do this straightforward computation and conclude this fact that h dot grad squared f of f at the point A plus T naught h is nothing but this big sum. Now this is looking a bit complicated, but if you think about it for a second, I can express this in terms of the Hessian. This whole thing is nothing but, this is nothing but h dot product, the standard scalar dot product, the Hessian of the function f at the point A plus T naught h. Now this Hessian is going to be a n cross n matrix. Recall that the Hessian is nothing but the matrix of partial derivatives di dj. It's going to be a symmetric matrix because we are assuming that this function f is C2, but for the time being that's irrelevant. This Hessian at the point, you can treat it as a linear transformation because it's an n cross n matrix and it eats up vectors to produce another vector. So I act this matrix on the vector h. That will produce for me another vector in Rn, and I can take the dot product of that vector back with h itself. So again, this is a straightforward computation why these two quantities are equal, and I'm going to leave it to you. Okay, so we have also assumed that gradient of f at the point A is 0 because we are assuming that it's a critical point. So the net upshot of all this is I can express f near the point A just using the value at A and the Hessian. F of A plus h is nothing but f of A plus half of this h dot product Hessian of f at A plus T naught h acting on h. Okay, I hope I have put the right number of parentheses. Now this quantity Hessian of f at A plus T naught h is annoying me a bit. I want to determine the nature of the critical point A using only the data at the point A. I don't want this T naught h term. So what I'm going to do is I'm going to somehow try to get rid of this T naught h term. So to do that, what I'm going to do is I'm going to see how much of an error I would make if I just replace this a plus t naught h by just I just ignore this term t naught h, and I want to see how much of an error I would be making. Okay, so what I'm going to do is I'm going to consider norm of h dot the Hessian of f at a plus t naught h acting on h minus h dot product Hessian of f at the point A. So this is solely to determine how much of an error I am making by replacing the term a plus t naught h inside the Hessian by just a. So I want to analyze this term. Now what I do is, first I notice that I can take the dot product outside and then apply Cauchy-Schwarz. I can say this is less than or equal to norm h times this difference of Hessian of f at a plus t naught h acting on h minus 1 second, I made a minor error in the previous step. I forgot a h. There's a h here also. Okay, yeah, so what this will lead me to is I would get hf a acting on h. Okay, so this step is just this inequality is just Cauchy-Schwarz. Okay, now what I'm going to do is, since I'm treating this matrix, the Hessian, as just a linear transformation, the natural thing to do would be to now use the properties of the operator norm and write this as less than or equal to norm h squared multiplied by Hessian of f at a plus t naught h minus Hessian of f at a, and of course this is the operator norm. Whenever you just have a norm and the quantity inside is either a linear transformation or a matrix, it's always the operator norm that I'm taking unless otherwise specified. So a bit soon I will intentionally start forgetting to put this op. Okay, now what does this tell us? Well, we know that the function f is C2 smooth. So the derivatives, the second derivatives of f at the point a plus t naught h will get very close to the second derivatives of f at a. So the net upshot is, if you fix epsilon greater than 0, and if h is sufficiently small, it follows that I can make that quantity, I can make this Hessian of f at a plus t naught h minus Hessian of f at a, this I can make it less than epsilon. Okay, so this just follows from the C2 smoothness. This is rather easy to show. Now the net upshot of this discussion is, I can write f of a plus h to be equal to f of a plus half Hessian of f at a. Oh, I forgot that h term. So half h dot product Hessian of f at a acting on the vector h plus an error term. Okay, so this error term occurs because I have replaced Hessian of f of a plus t naught h by just Hessian of f. But since we have chosen h sufficiently small such that this inequality is true, you can easily check that E of h will be sublinear. What I mean by that is, E of h by norm h squared goes to 0 as h goes to 0. This error term is quadratic because of this inequality. Okay, now because this error term is small, we will be able to get some useful information about the behavior of f at the point A. I'm going to come to that in a moment, but let's just focus on this particular key term, this h dot hfa h. So this seems like an elaborate way of writing that one term, and since I'm assuming you have taken a course on linear algebra, some of you might have already recognized what this quantity is going to be. Well, recall that HFA is a real symmetric matrix. It's a real symmetric matrix. So it defines an inner product. Rather, it may not define an inner product, it just defines a bilinear form. Inner products, usually we assume positive definiteness, if you recall. So this Hessian, for the time being, since it's just a real symmetric matrix, all I can say is it's going to define a bilinear form. How is it going to define a bilinear form? It's going to define it in this following way. V comma W just goes to V transpose HFA W. Okay, where I am treating the vectors v and w as column vectors, so I'm taking a transpose to make it a row vector, and then I'm acting the matrix Fa on w. Of course, what I mean by this is I write down v and w in the standard basis. I write down the coordinates and do this computation. This will turn out to be a bilinear form. So the term that we are interested in, H dot product HFA acting on H, this silly term is actually nothing but H transpose HFAH. Okay, so this is just taking the inner product of H with itself, not taking the inner product, taking the bilinear form HH, where the bilinear form is the bilinear form determined by this real symmetric matrix, the Hessian. Okay, so there is a name for this. It's called a quadratic form. I hope you're familiar with it. If not, the main result that I need about quadratic forms, I'm going to do it anyway in the next video, so no problem. So let me just state the definition on a fresh slide. So this is the definition of a quadratic form. Definition of quadratic form. Okay, a polynomial of degree 2, let's just call it Q, from Rn to R is called a quadratic form. Okay, so the definition is utterly straightforward. In fact, you could have guessed what it is just from the name. So the key part is that symmetric matrices determine quadratic form. If A is a n cross n symmetric real matrix, then it determines a quadratic form, given by X maps to, again, X transpose A acting on X. That this is going to be a quadratic polynomial, it just follows from the very definition of matrix multiplication. Now the key fact that I need is this quadratic form being positive definite or negative definite or indefinite. A quadratic form is said to be positive definite if Q of X greater than 0 if X not equal to 0, negative definite if Q of X less than 0, X not equal to 0. Okay, it is said to be indefinite if it takes both positive and negative values. Okay, now I'm going to prove a theorem that characterizes the nature of the critical point using the nature of the quadratic form determined by the Hessian. So the theorem is as follows. I am sure you would have used this theorem, at least the special case when n equal to 2 or 3, in a basic course in multivariable calculus. So the setup is as follows: f from BAR to R is C2 smooth, and A is a critical point. Then A is a point of maxima if this quadratic form Q of x, which is just by definition equal to x mapping to x transpose Hessian of f at a x, is negative definite. Note this weird role reversal. You might think that maxima means things should be positive, but no. At a point of maxima, this quadratic form should be negative definite, and this should actually not be shocking to you, because if you go back all the way to kindergarten when you studied maxima and minima of one variable functions using calculus, you would notice that the second derivative has to be less than 0 at a point of maximum, right? So, or rather the other way around, if the second derivative is less than 0 at a critical point, then it's a point of maximum. So this sort of generalizes that basic fact from elementary calculus. In a similar way, if Q is positive definite, then Q is not Q, A is a local minimum. If Q is indefinite, then no prices here for you, then A is a saddle. Okay, so we are going to prove this. Most of the proof is already done in the discussion above. Let's just finish up the details. What we have to do is the following. We already know that f of a plus h is f of a plus half the Hessian of f at a. Again, I keep forgetting to put, let me just put q of h. Let me be lazy, I have earned that right. Plus the error term. Okay, and we know that this error term is small. It's sublinear. This quantity goes to 0 as h goes to 0. Okay, now we are going to just prove one case and leave the analogous case to you. I'm going to assume Q is positive definite and end up proving that this is a point of local minimum. I'm going to leave the negative definite case to you. Now, what this means is that Q of h is of course greater than 0. Okay. Now Q is continuous. As Q is continuous and positive on Rn set minus 0, it must attain a minimum on the unit sphere in Rn, right? The unit sphere is a closed and bounded set. The unit sphere is a set of all points in Rn that are precisely distance 1 away from the origin. This unit sphere is of course a closed and bounded set. Therefore, by the Hein-Borel theorem for Rn, we know that it's going to be a compact set, and we have also seen that continuous functions on compact sets must attain their maxima and minima. So it must attain a minimum value, and this minimum value, this is the key, this minimum is strictly greater than 0. Because it does not take the value 0 at any point on the sphere, this minimum must be strictly greater than 0. So I'm just going to call it, say, m, little m. Okay. Now what this essentially means is that Q of x is Q of h q of any vector h, this is going to be greater than or equal to m norm h for all h in Rn. Okay, why is this the case? Well, actually this is going to be norm squared, m norm h squared. Why is this the case? Because what will happen is, if you know that q of h by norm h, this will be greater than or equal to m, simply because h by norm h is a unit vector. Now if q were linear, I can take this norm h, 1 by norm h outside, but q is in fact quadratic. It's a quadratic form, and just by the definition of q, you can immediately see that this norm h, two of those norm h's will club together and produce a 1 by norm h squared outside, which I have just taken to the other side. Okay, so this is a trivial proof. Just look at the definition of q. It's just h transpose Hessian times h. When you replace h by norm h, there will be a 1 by norm h squared sticking outside. Just shove it to the other side. Okay, so we have that q of h by norm h, or rather, let me just erase this. We have q of h is greater than m times norm h squared, and this is true for all h and Rn. Okay, now what you do is choose h so small that norm of EH is less than m norm h squared by 4. Okay, this can be done again because E of h by norm h squared goes to 0. Therefore, norm E of h by norm h squared also goes to 0 as h goes to 0. The error term is sublinear. Okay, so the net upshot is f of a plus h will be greater than f of a plus m by 4 by norm h squared. Okay, check this. Wait a second, I made a slight error here. Somehow the norm h squared came to the denominator. This is m norm h squared by 4. So I want you to check this. Check how we got this. It's rather easy. I've just analyzed the fact that this q of h is going to be at least m norm h squared. There is a half q of h, so there will be a by 2 here, and I'm just going to combine this E of h term with this m norm h squared by 2 term and see that it's got to be at least m norm h squared by 4. Okay, so this shows A is a point of local minimum. Okay, so I'm going to leave the proof for you when the Hessian is negative definite. I conclude that A is a point of local maximum in the exact same way. Now, one case remains. Suppose Q is indefinite. What this means is that it takes positive and negative values on Rn, but because Q is a quadratic form, you can scale a vector x where Q takes a negative value. So if Q of x is less than 0, you can easily see that Q of Tx will also be less than 0, where T is any real number. So this just means that there are vectors of any given length at which Q is positive and at which Q is negative as well. The moment there are two vectors x and y, where at one point Q of x is positive, at the other point Q of y is negative, then I can just scale these vectors around and continue to get vectors of any length that I desire at which Q takes positive values or Q takes negative values. So what this means is I can find unit vectors x and y such that q of x is less than 0, q of y is greater than 0. Okay. Now what you do is set m to be the just set m1 to be q of y and m2 to be q of x. Okay, and set m to be the minimum of these two values, not just the minimums. M1 comma minus m2, set it to be the minimum of m1 and minus m2. Okay, now we use the observation that I had said before, that when you scale the vectors by t, when you scale x and when you scale y, you can predict the value of q of tx and q of ty. From that, a very simple computation will tell you that f of a plus tx is greater than f of a plus m divided by 4t square. Okay, and similarly you can conclude that f of a plus ty, I think I got the inequality reversed, this is less than, and I can conclude that f of a plus ty would be greater than f of a minus m by 4t squared. And note m is positive by the way I have defined m. Okay, and this is true. This is true for all t. This is true for all t. Hence a is a saddle point. Okay, so this concludes the theorem. The proof is not hard. It's just involves simple inequalities once you know the behavior of the Hessian. Now you might be wondering what happens if instead of positive definite I have positive in semi-definite. That means q of x could be 0 at points other than x, but q of x is always greater than or equal to 0. What happens in that situation? What happens if it's positive negative semi-definite? Q of x is less than or equal to 0, but at some point it is in fact 0 and x is not 0. What happens to these cases? Well, you can't really predict what happens, and there's an exercise in the notes where I give you three example functions and ask you to work out what happens to these functions at the critical point. Okay, so this is essentially determining the nature of a critical point using the Hessian. Still the question will arise, if I am given this Hessian matrix, how do I know whether it's positive definite or negative definite? Well, one criteria, if you have taken a sophisticated course in linear algebra, not just a basic first course, you might have heard the word spectral theorem. If you have learned the spectral theorem, this will be rather easy to show. You can show that this quadratic form will be positive definite if and only if all the eigenvalues are greater than 0, and negative definite if and only if all the eigenvalues are less than 0, and indefinite if and only if some eigenvalues greater than 0 and some eigenvalues less than 0. So the spectral theorem will immediately tell you how, and determining the eigenvalues is not that hard. It just involves some computation, at least in the 2 by 2 and the 3 by 3 case, which is mostly what we are interested in. In those cases it's rather easy, but for sophisticated applications like the thing that Google uses or NASA uses, you will typically not be dealing just with 2 by 2 or 3 by 3. So there finding the eigenvalues is not so easy. There is another elementary way of finding out whether a particular quadratic form is positive definite or negative definite. That's by what is known as completing the squares. That's an elementary way of seeing whether a quadratic form is positive definite or negative definite. We will see that in the next video. This is a course on real analysis, and you have just watched the video on criteria for extrema using the Hessian.